Hi everyone. I keep forgetting just how much stuff we have when it comes to the review. I want to make sure that we have the review. If you want to do the review, you do the review. If you don't, if you think you're comfortable, then fine. So again, just a preamble. If you're very comfortable with C coding and you know how malloc works and you know how to arrays work and pointers work, you should be feel fine. But I want to make sure that I'm thorough enough that people that are not comfortable with some of the earlier course material feel a bit more comfortable. And if you're really unsure, again, don't just watch the videos. Play around. Get a basic, project going, and just try some of this. It will make a huge difference. Rather than just passively letting this information roll over you, try some things out. You are not going to break the computer by trying out different code. So the act of doing is one of the best ways of learning. So try what we were doing last time. Try some mallocs. Try some news. Try dealing with pointers. Right? Not just on a piece of paper, although that helps too, but try coding it up. Preprocessor directives, though, are one of those things that a lot of people sort of either ignore, they hope they just go away. I don't know. Because I know I worked on it a lot. I know Chris Jocelyn does it a lot, but I think other instructors have not necessarily looked at those. I end up calling them macros. They come up in weird, wonderful ways and not so wonderful ways as well. This is anything that starts with that hashtag or that pound sign if you're old like me. This is not compiled code. This is something that will be done before I get into actually compiling my code. So pretty much every single time it does this, it will, if I'm defining some value, it will define it before I compile my code. I can do a bunch of tests before if I want to. You'll actually see this at all our header files. We'll have an if something is defined, then do this, otherwise do that. We can define individual things. So we can say define. Heck, you can just say define foo and just leave off that, and it will be defined. It just you don't know what it's defined as, but it's defined. And we can check if it's not defined, undefined, if it is defined, and if I have an if statement, I can check to see if it's defined, this is the end of my if statement. So like an if statement with the curly braces, I have an if and then an end if. This ends up being useful in a lot of ways, but we've also done a lot of includes. So okay, assert.h like we did last time. That will take everything from assert.h, the entire file, all the text from that file, and just dump it on the top of your program. That's what it's doing. That's what these precompile directives are doing. I can also define certain things. So I can define a value as something. I can define, let's say, let's change it to let's call it mypi and 3.14. And you might say, why not a constant variable? And I'd say, sure, that's fine, right? The constant variable, some people swear by doing this because instead of putting a variable in or referring to a variable, I am literally everywhere I see the word mypi in my code, every single place the word mypi is, this number gets stuffed in instead before I compile. I don't have a variable at all anymore. I am literally just finding and replacing everywhere with the word mypi with 3.14 in my code. As a mass find and replace, that's what a define does. If something, and I can check to see if something's defined or not defined. So here's me defining the size as 200. I can define something and essentially do an instruction. So everywhere I have some and some variable a and some variable b, it will add a and b together. So I could say sum for 3, and it's going to act and look exactly like a function call, except it's actually going to be 4 plus 3. It's going to just plop in 4 plus 3 instead. Where this is, it gets wiped out and it becomes, and then on top of that, then it will actually calculate 7. I can check to see if size is defined. If size is defined, Then I will do this, and then I will stop. I will can undefine size, so the size is no longer defined. And then uh, this will still end up working. Is A and B defined yet? No, so there's no variable A and B. This won't actually compile. But so these preprocessor instructions can be extremely useful. In fact, they become most useful around here, the header file. The header files end up being in a whole lot of different places, and we're going to see C header files. We saw, I think you see them in 1400 as well. You're going to see a lot more of them here in this class. The C header file is your table of contents. You don't define many things in your C header file. It is just meant for, by the way, I'm going to have these functions around. Much like our prototypes, I'm going to have these functions that people are going to be able to use. That's what assert.h is. It's a header file. It is, here are the functions that assert defines. Are they defined there? No. They're just, these functions are available to you. And somewhere else, the functions themselves are actually defined. The header file is on page 2, that's where you'll find this. On page 17, this is where you'll find that. The header files are included in a lot of these functions just so that they know, so your different chunks of code know where other stuff is. So it allows you to just include where other things are defined. We're going to see a lot of this when we deal with objects. They're everywhere with objects. We don't really need this at all. If you only have one file for your entire program, you're done. You're good. But when we talk about objects, each of your objects is going to have a lot of your objects are going to have a header file, and that header file has all the different functions and all the different variables for that object. And then you need to be able to put that header file in all of your other functions or in all of your other classes. So here is, I'm going to include standard IO. If I'm doing that, it means the standard IO library is pulled in. The header file itself is directly dumped into the top of this source file.c file. And if I call printf hello, it says, okay, what's printf? Well, it's defined in here. There's a prototype for printf in studio.h, standard.io.h. So printf, there's a reference to it there. And where is that? Oh, it's in standard.io.c .lib, the library for standard IO. So it allows you to find where things are. The header file is the intermediary. It's a table of contents so you can find out where this thing is. And so as a result, by doing that include, it allows me to include other libraries or other code. I'll also do one other little thing. This is the old, we'll talk about it again soon, but this is the old school way for every header file. Let's call this header file myheader.h. All right, we'll have something like this. I thought this was so cool. Maybe I'm just a nerd. Old school way and if. Old school way of doing a header file. What is this actually doing? The top line says, if I have something called myheader_h, if something like this is defined, which hasn't been defined yet, by the way, but if something like this has been defined, or it has not been defined, then define it, do a bunch of stuff, and then finish. So the first time you include myheader.h in one of your files, you will define myheader_h. You will say, is it defined? No, it's not. Define it, do a bunch of stuff, include everything, stop. The next time another class tries to include myheader.h, what happens? It says, is myheader_h defined? Yes, it is already defined. Stop. And it skips all of this. which means all of this stuff gets included one time in your entire program. It doesn't get included in every single CPP file. It gets included once, which is is critically important just in how everything builds up. This allows you to include that header file one time, but everyone knows how to use that header file. The first time it's a first use, or the first class to try and include that header file includes it, and every other class then just uses it later. We'll look at it later, but this is where where precompiled headers come in handy. This also, you'll see there's a new terminology for this instead. It was, oh, I always forget what the term is. We'll look at it again. Uh, there is include once, or there's a special new term for it. That's not it's not a precompiled header. But so uh, hopefully this is just going to be our last day of review. We're going to look at input and output. We're going to look at structs a bit more, and then we're again going to look at debugging just to see how we can look at things. I didn't actually update this slide, I don't think so. But the exam should be coming up very, very soon. It would essentially be a review of BIT 1400. Uh, the first assignment should be due very, very soon, so make sure you're doing it. Make sure you did A1A as well, right? You have 2 weeks to do an assignment, but you cannot do it the night beforehand. Do not even try. And the exam itself, make sure you bring a cheat sheet, or make a cheat sheet. I know it's an online exam, you have a textbook in front of you, but the act of making a cheat sheet, the act of putting down the information that you think is critically important and examples that you think are important, is part of the studying process. It's going to take too long to go searching around for how to do something. Put an example down. Most of the time, you don't even need the cheat sheet afterwards, because you'll remember because you've actually done that. Okay, but make sure you practice a bunch. That's what we're making sure we do. Okay, so input and output. We have done scanf and printf. We're going to be looking very, very soon at cin and cout, but we can't do those yet because they are actually objects. We haven't done object-oriented programming yet. So you'll also notice that Visual Studio, I think, has printf underscore s and scanf underscore, definitely has scanf underscore s. That s is for secure, or potentially for safe, or something along those lines. It's ambiguous what the s is actually meant to be representing, but it's essentially safe or secure. So the syntax is slightly different than what we had before. We have different ways of formatting our strings. So we may have a %d for a decimal, %i for an integer, for a decimal value, %f for a float, %c for a character, %s for a string. That's for a C string. And we have an escape character if we need to. So /n is for a new line, /t is for a tab, for example. Anything you don't know how to do, if you can't type it, the slash is probably there for it. Look it up if you hit those situations, but /n and /t are the big ones. How do you put a slash? So how do you put this backslash if backslash is for an escape character? Okay, so some of you already know. It'd be // Right, that's the way to work around it. Scanf, on the other hand, and if I want to take in variables, scanf is really weird. I don't really love scanf, but it does what it needs to do. So scanf is using variable addresses. It is actually using pointers like we were doing before. So hopefully I have an example of scanf. Here's scanf in action. I would not normally do it two at the same time, but I'm going to get I'm going to get a digit, I'm going to get a digit. That's what this is saying. Two numbers in a row. I cannot have any other text in here other than white spaces and new lines and the like. I can only have what I'm going to be taking in with a scanf. It's going to put the first number you type in into variable I. I give a pointer to I. And then I'm putting the next number you type in into J. I'm giving a pointer to variable J. That's the only way. Remember, this is a function. And the only way I can pass data into the value, modify I and J, is if I pass a pointer to I and J. I can't just, if I just put I and J in there, it'd make a brand new variable, and then that variable would go away at the end. The only way to directly modify I and j is to make a pointer to I and a pointer to j, and then modify them directly. So that's why we have this and the and here for scanf. Printf will make this string everywhere it has one of these percentage d's or percentage n's or percentage c's. It's going to say, okay, I'm going to be plugging some value in here. So I'm going to plug in some value here. I'm going to plug in a value here. The second parameter, plug in a value here. Third parameter. First parameter is going to be whatever I is. Plug that in there. It's going to be I plus j is equal to whatever I plus j is in terms of a value. So let's say I did this all over again. Scanf would take, and I put in 4 and 3 for j. So I is equal to 4, j is equal to 3. Let's put 4, 3 here. What I'll end up printing out is 4 plus 3 is equal to 7, and then a new line. The right way of doing it, and why I had a second thing and I want to overemphasize, is for the love of God, do not ask for a scanf if you do not tell people what to type in. It is bad design, right? If you do not tell people that you're supposed to put in two numbers and then press enter, how the hell are they supposed to know, right? So you put some message at the beginning, enter two numbers, then press enter, for example, right? So now people know to put in a number, maybe a space, and then another number. And then it'll print out what you're supposed to. When we do cout and cin, couts and cins work very similarly to printf and scanf, right? This format's slightly different, and you've probably seen this in your textbook, but this is C++ code. This is the output stuff goes, follow the arrows, into the output to the screen. So this message goes to the screen. This message, the end line, goes into this message, which then goes to the output to the screen. Cin goes from the screen to the number. You can follow the arrows. The number that gets typed in goes into the variable j. And then finally, this end line goes to gets attached to the j, which then gets attached to the and, which gets attached to the I, which gets attached to this, which then goes to the screen. So what ends up happening? Enter two numbers and press enter is the message. You enter a number, and then it prints out the values entered were, if we did 4 and 3 again, the values entered were 4 and 3, new line. It's exactly the same message we had last time. Okay, let's hit structures briefly. So what the heck are we talking about with structures? Because structs are a little bit quirky. When we do linked lists, we'll see the structs in action. Very much in action. So a struct, much like an array, is a contiguous chunk of data. The difference is that it's an aggregate chunk of data. It is not a bunch of integers. It's not a bunch of characters. It is just a bunch of variables stuck together, like duct taping your fan to your computer, or duct taping two things together. You take a bunch of variables, you duct tape them together. Hey, you got a struct. Congratulations. They don't have to be the same type. They don't have to be anything related to one another. They are just a way of wrapping a bunch of variables together. So they can contain different types, and you don't go to like element 3. You go to individually named elements. You can combine them with pointers, and you can do all sorts of crazy things. This is the key part, right? If we have arrays, pointers, and structs, we can do almost anything in computer science now. Because we can make our own data type, which then we know it has pointers, which then has an array, which then has, then you can do really interesting stuff. So here would be a given struct called student. It's going to have an array, which is a character array or name, right? So this is going to be an array of characters, and we'll talk about character arrays in a second. This is ding in /0. Oh wait, that's a special character. This is an alternating character. It's our character that we know we got to the end of the string when we get to this thing. So even if the array has 4,000 elements, The fifth element is this. That's the end of our text string. Okay, so this is an array. This is going to be an array. This is a pointer to the front of the array. A pointer to the front of this array. Two different arrays. It's going to have an integer ID, and it's also going to have a floating point number as well. There we go. So if we make, it will reserve all the space in memory. It will reserve a pointer. The size of the structure is the size of a pointer, which I think is going to be 64 bits. The size of a pointer. It's not the size of the array, by the way. It's just the size of the pointer itself. The array has to be stored somewhere else. So it's the size of a pointer, plus the size of a pointer, plus the size of an integer, plus the size of a float. And that's going to be the size of this structure. If I do a size of for a student, you will find out how big this structure is. The structure itself, just doing this structure definition, that is not making a student at all. This is the blueprint. This is what a student will look like if you make one. It is just the how you can define this new data type. You haven't made an instance of that data type. So this is what I'm thinking Elon Musk for some reason. All right, he comes up with these, the Hyperloop and all this kind of stuff, all these ideas. He didn't implement any of those yet. He did some of the space stuff so far, but just the idea itself is not the same as the implementation. The implementation is a whole other thing. This is how I would do a Hyperloop, or this is how I would do this student structure. I have not made one yet. So a human looks like this. This does not mean that you made a human, or I name something. I'm trying to think of a good example here. Let's do the Hyperloop, right? This is how a Hyperloop would be defined. I haven't made one, but when I do make one, it's going to have these characteristics. We'll see this in action when it comes to a linked list. We will have a node in our linked list, and it's going to have different attributes. And when I make a node in the linked list, it will have those attributes. So I'm going to make a student named Ali. I'm going to set the ID for Ali, and notice I'm doing this. I'm using the dot to indicate for the student Ali, the ID is going to be equal to 0. I can also say I'm going to make two different things. I'm going to make a student named Ali. I'm also going to make a classroom of students. So full classroom of 20 students. This is an array of 20 students. I could put this on two different lines. Student Ali, student classroom 20, an array of 20 students. And I'll make an array of 20 student structures if I wanted to. So I could then, let's just throw this up here. I could say classroom for the fourth student in the class. That looks like a 9. Let's do, there we go. Dot ID. This would be the fourth student in the class, 0, 1, 2, 3, 4. So at index 4, that student and their ID. Let's give it the number 17. That student has ID 17 now. Right? Student 3 doesn't have that ID. Student 2 doesn't have that ID. The student at index 4 has ID 17. That's what that's going to do. So we'll do a quick quiz about how we actually define or use a struct to hopefully get a sense of how they are useful and how you access individual elements. Okay, so try the quiz right now. Hopefully it should be up and running. I'm so nervous about setting these things up for you guys and not forgetting to enable the quizzes for you guys. But you should have a quiz available to you. If you don't see a quiz available to you, make sure you Piazza post to make sure I get the quiz up and running for you guys. Okay. I think we already talked about some of these common errors, so maybe we won't go excruciating detail on this. I didn't have time normally in classes. Notice at our comments, we have comments, two types of comments. We have this and we have this. The common error is you accidentally forgot to include the closing comment, and you just everything on your code gets commented out. Very common mistake. Um, or starting a comment with the characters this instead of the other way around, fairly common. Um, you forget an F in printf. You use a capital letter and lowercase letters interchangeably. Keep a consistent naming scheme and writing scheme for things. Don't write main with a capital M. Don't name your things student with a capital S and a lowercase s in some other cases. Um, sometimes some people reverse the left and the right side. The left hand side is always where things get assigned to. The right hand side is always what you actually do, what you're calculating. Um, if you forget the ands for scanf, that's a very common error. I still make it to this day. And a lot of people confuse double equals and single equals. This is assignment, single equals is assignment, double equals is for equality. Is this equal to this? If so, do this other condition. Not having the correct number of opening and closing curly braces is also a big deal. And generally, for every one of your functions, you want a comment at the front. What goes in, what goes out, what's this function used for? No one wants to read your function. They just don't. If you look at everything that your professors give you, if you look at what your friends do, if you look at almost anything you do in your life, you do not want to read most of the stuff. And most of you, myself included, just get lazy about it. We have too much stuff to read. So when we get Google responses, like if you do a Google search, what do you get? You get a whole bunch of headers for what the heck is at that website or what that link is going to go bring you to. You scan over those things and figure out which one you want to click on. You're not going to read the whole thing. You want something quick and dirty so that you can actually understand what the heck this thing does. No one wants to read your code. They want to see what the thing does, what the function does, and stop there. So you can add, if anything that's going to be confusing, but anything at the bottom of your curly braces, put a comment saying what that matches up with. That's a little old school, but you could still do it. Definitely works, right? When you close that parentheses, is it the end of an if statement? Is it the end of a for loop? Is it the end of this, end of that? And if you don't know what the heck that comment is for, like what that code is for, you should expect a comment. Your indentation, for the love of holy, make sure that that indentation is right. Don't fight this. Don't fight the ID. Don't fight Visual Studio. The indentation tells us how to read this, and whether your code works or not, if I cannot read it based on the indentation, I cannot help you with your code, and I won't even. I may not even try bothering. Right? Your indentation allows me to read code in much, much, much faster way. Normally, you want to use meaningful and less than 31 character identifiers. There are a whole bunch of weird conventions. So we have IJK for indices, X, Y, Z, fine, or Z. We have A underscore my array or my nums or something, whatever the case is. This is not necessary, but just have some kind of convention that works for you. P underscore. This thing is called Hungarian notation. It tells me, hey, by the way, this is a pointer. It's not an array, it's just a pointer to one variable. This is telling me, hey, it's a pointer to an array of variables. And if I have a whole bunch of variables, I'm not going to remember what all of these variables do. I want to be able to tell from the variable name. This tells me it's an array of numbers. Great. I want that, right? I want things that are short and sweet. My personal favorite one. There's no way anyone's going to get this, but let's try what the heck this is. Computer scientists are efficiently lazy. We have a convention for this. And is it L18N? Ah, damn it. I'm not going to remember the exact numbers. I'll have to look it up just to make sure that it's 18 in this case. I18N, if it is 18, it could be 23 or something like that, stands for something. Stands for internationalization. No one wants to write out that big long word, so as a convention, across the board, across industries, we will use, for localization, it is how long the word localization is. There's 18 characters in between, and it finishes with an N. So internationalization, and it's by convention that across the board for people using that. Same with localization. Just we have meaningful, consistent names that other people can read and understand what you're doing. Even if it's short form, we have a way of, as long as you're consistent, people will understand it. Um, you want to separate your definitions and your execution of statements in a function. So I define a bunch of variables, then I do something afterwards. I do those at the same time often if I know, or I'll set it to safe values. Uh, I normally put a space after each comma, make sure it's readable. Your spacing actually is a big deal for readability. And people will actually, at Google, at CDDAPGO, at every company I've ever worked for, they will throw your code through a lint checker. So essentially, they'll throw it through a system that will check the formatting of your code to make sure it's formatted in the right way, consistent to the business that you're in. So if you throw it through the lint checker for Google, it will tell you if your spaces are in the wrong position, if you added two spaces, if your semicolon is in the wrong place, if your curly braces are not lined up, that sort of thing. And people will reject your code and tell you to redo it all over again if you don't pass that checker. People are extremely picky about the code formatting because it allows you to read. If you write an English essay and it's just all over the place and there's no structure to the look of it, you don't. If you have two paragraphs and they're just stuck together, there's no space in between. You don't know they're two paragraphs. So people are very, very careful about this. Um, your compiler will actually add the closing parentheses as soon as you open the opening one, so that's useful. And from my personal standpoint, even if it's optional, even if it's just one line, put in an opening and curling parentheses. Just do it, please. It will save you hours of work. And I've caught enough students when they said, "Oh, I don't need to do that." And when I finally find out their bug, half the time it's this, right? They put an extra. They had one line in there, and they stick in another line. It's indented, so they think it's part of that for loop. It's actually in a different thing. It's harder to read. So make sure you include your curly braces. Um, so how do we debug our code? How do we debug it in 1400? I normally would go on the whiteboard and talk it out with you guys. We don't have that option right now, so let's. I want you to think about it. What did you do to debug in the past? Well, some of the things we could do. We had. Do I have it in here? All right. Well, some of the things we had. We had printf statements. That's the standard. That is the brute force ignorance approach. I do asserts everywhere, right? If my code blows up there, I know that there was something wrong with that number, and therefore I can trace it back. I might do breakpoints, figure out where I stop in my code, and see, and look at the actual individual variables. I might look at what the output of my code is and see if it's formatted correctly. I might have a bunch of test cases. I might have integration and unit tests. There's a number, or I can just look at my code in general. These are all approaches to debugging. But the one thing you can't do when you're fixing your code is just throw your hands in the air and just give up, right? That doesn't solve the problem. So the actual solution is methodically, and it's a pain in the ass, and everyone goes through this salt mine. So if you think you're taking a large amount of time, yeah, you are. Everyone does. You have to go through that pain point, but it is the most gratifying thing in the world when your code finally works. It makes it all worthwhile. I always think of it like actors. Actors will go through absolute hell preparing for a play, let's say, and they're not being paid hardly at all for most times, especially if you're doing amateur theater and you're spending so much time preparing things and it's all very stressful. And then you get on stage, when you get off the stage at the end of the night, especially if you have a good night, suddenly all of that pain is just ignored and you're ready to do it all over again. You're ready to go through that hell all over again just for that hit, just for that feeling of that sensation of being on stage. Same thing with coding. When you finally getting it running, it is the greatest feeling in the world. So you can add debug code. We had printf things, but there's other artifacts. So if I'm doing a VR system, I can't do printf statements. So what do? I put something like, if I want the frames per second in a game, I could put it on the screen itself. Or I can put little vectors in my VR system. I literally did that for the VR system I did for my master's degree. So I could see where the arrows were, where things were rotating. It was the only way to figure out my system. I spent like 6 months just floundering, and then found out if I put this thing in there, I could figure out what was going on wrong with my code. Um, so you can also do timing and timestamps, so you can log your data if you want, but that can sometimes be unreliable. But it's critically important to be able to debug or output some stuff. You can also try, and this is something people don't do enough of, I don't think, is just commenting out code. That's not deleting your code. You never delete your code. You look at your code, you you don't know what's going wrong with it, comment out a line or comment out a function or change your function slightly but keep your old function just in case you need it again. Check what happens. So you don't know what so if when my air conditioning, let's say in my house, is there's making a weird noise, what do? I go up to the air conditioning vent, I kick it and see if the noise stops, right? That's essentially what you're doing. You're kicking your air conditioning system, seeing if the noise stops. So in this case, I comment out some code. Does it change things? If I comment out that code, does everything fix now? Do I suddenly get the wrong answers? What happens? And I can try and trace back what's going on with my code just by commenting out something and seeing what happens. I can put asserts in my code just to make sure that the we're not doing unit tests and integration tests. That industry does those everywhere. Like literally half the code that you write, if you're writing server-side code at Google, more than half the code you're writing is integration tests and unit tests, not the actual code itself. They have coding in what is it? Testing on the toilet and coding on the can and a bunch of other little terms for it. But essentially, they put posters up for how to debug your code in the bathrooms at Google, just because it's so critically important to make sure that you can test your code correctly. An assertion is the simplest, easiest way. An assertion is this better not be the wrong value. If it's the wrong value, blow up. There's something terribly, terribly wrong, right? The index I'm going to is a negative value. Holy crap, that's something terrible. Blow up, right? You should never get an index value that is a negative value. It's 0 or more. So assertions are just one form of that. And you can also use the debugger. You can breakpoint and look at your code itself. And then there's just thinking about your code, just looking at your code line by line and thinking about it. I love Brian's quote on this for Unix for Beginners in 1979. The most efficient debugging tool is still careful thought coupled with judiciously spaced print statements. And it's still being used today. It is amazingly effective. Just put a bunch of print statements to see what the values are, right? If you don't know what the variable is, print out what the value is and see what it looks like. And then you can figure out what's going on. And it just methodically breaking down big problems into small little chunks. That's debugging. That is not compiling. If it comes to compiling, it is to start at the top and work your way down. Line by line, see what each of the errors are, and just look around to see if you can figure out what the problem with your syntax is. Okay, so the debugger allows you to control the execution of your program. You can go line by line. It doesn't always work for all cases because it throws off the timing a bit for video games, for example. But the program is created with and without debugging information, and so you can do different builds. The debugging build allows you to look at it line by line, which is very, very useful. And we've already looked at using the debugger before. And we've looked at that. So what are the main steps for building a program? What are common variable types in C? How big are those variable types? How do pointers work? How do structs work? How do arrays work? These are all things you should be able to answer before you go to that exam. How do you define a new function? What goes into a function? What comes out of a function? How do functions work? Why do I use a function? And why do we use iteration and decision-making programs in a function? Like, how does a for loop work? How does a while loop work? When do I get an infinite loop? Honestly, the best way to study is just to code and program. You cannot memorize this stuff. Much like a math class, you don't memorize your math class. You learn just enough to be able to apply it, and then you practice applying it. You also don't learn to play the piano this way either. The way you learn how to play the piano is you play. You learn how to play basketball by playing basketball or doing drills. Watching tape does not get you up to the level of the MBA, right? Watching tape just is one small fraction of what you need to do. The main point is you have to actually do it. You have to practice. And so practicing for that exam, practice. That's the big thing. The assignments themselves are there to help you with that practice. Okay, when we come back around next time, we'll deep dive into C++ soon. A1B is coming home, is about to be done soon. A2 is going to cover new material. It's going to be talking about objects and strings. Hopefully, I have this on the next, and we have some further reading if you want to look at some of this uh, open courseware for object-oriented programming and other interesting things about object-oriented programming. Um, but, so I don't want to jump ahead. We're going to look at the linked list. So, um, we pretty much have a term long thing, and I was going to start the slides there. No, I'm going to make it another presentation. We are going to have a term long metaphor or a term long example looking at linked lists, and we'll talk about those very soon. This is data that connects to other data that connects to other data that connects to other data. It's chunked, there are chunks of data that all connect to each other, as in a conga line of data. When we come back next time around, we will look at linked lists. We will implement a linked list in straight C and see it in action. And hopefully that will also help you prepare for the exam as well. I'm going to make sure that you have that available to you for the exam. And then after that, all material after that, when we talk about object-oriented programming, that's all going to be all new stuff for after the exam. Okay, but the slides on the presentation on linked list will hopefully also be useful for preparing you for the exam. Okay, with that, I'm going to take my leave for right now, and when we come back next time, linked lists. It'll be exciting.